my screen. Right, so we have spoken about lots of things. But now we are more onto the detection side of things. And let's have a look at what our sensors are and what the difference is between them, or is this significant or what? So what is a good sensor? Here we have 3 photons coming in, and they arrive at the sensor. And clearly what we would like is that the sensor detects all 3 photons. But look at this. This sensor is only detecting 1 photon. Okay, so, and then I'm not going into the photophysics of the whole thing. Very simply, when one photon comes in and is detected, then it's sort of transformed into 1 electron inside the sensor. And then there is an amplification process. So instead of having 1 electron, we now have many electrons. And then finally, all these electrons, this is electricity, right? So we're reading the voltage. And so we're getting this voltage. A voltage is an analog signal. So it means that we can have any value in our voltage. And finally, we have a digitalization, which is what we have been talking about this morning. So we have a conversion from this analog signal to a digital signal where we have a finite number of integers. So finite numbers of integers. And this is done by the analog to digital converter in the sensor. And so we get a digital image. The analog to digital converter reads the thing and says 1. And we get 1 pixel of 200, for example. That's the intensity. And we construct the digital image. So it's pretty much the same type of same type of process in cameras, and this is different, but more or less the same type of things happen in cameras and in so in each pixel of the camera and in the detectors that we have on single point confocal. So what do we want from a good sensor? We would like it to be very photon efficient. So we'd like when we get 3 photons to detect 3 photons, but it doesn't happen that way. And then we would like it to be very efficient at amplifying the signal, because these signals are very dim and we need to be able to read them. So we need to pass a certain threshold. We need a good amplification. And then we would like this whole process to not influence the signal and not add its own noise on top. And then we would like the whole thing to happen super fast, clearly. And then we would like to have a high resolution and a high dynamic range. So high resolution, now you know that for a camera, what it means we would like to have small pixels, but we'd like to have also a high dynamic range. So I'm going to talk about this. So the photon detection, how efficient the photon detection is, depends on the specification of your sensor. So once you have the sensor, you can't do much about this. But everything else depends on the settings, and that's good. It means we can influence it. It also means that we need to know what we're doing when you're setting the things. So in this lecture, I'm going to talk about this and about a little bit about speed very briefly. So what about the sensitivity? We have 3 photons, we detect only 1 photon. Why? Because we have a certain quantum efficiency. So the ratio, the percentage of incoming photons that trigger a signal is called the quantum efficiency of the sensor. So if we have 3 incoming photons and we only produce 1 electron, so we only detect 1 photon and we transform it into 1 electron, we get a quantum efficiency of 33%. The quantum efficiency is very different from one type of sensor to another. So here you can see a few detectors. So this is in single point confocals, and a few cameras. So these are some very typical cameras and single point confocals. And here you can see the maximum quantum efficiency. So I will explain why maximum. You can see that in a conventional PMT that you can find in a single point confocal, only a third of the photons actually lead to something in the camera. or in the detector. So that's 2/3 of the photons are simply not detected. That's not very good. Even in the GASP Heidi, which have the top of the cream or something like this, 45%. So more than half of the photons are not detected. And that is the maximum quantum efficiency. So we will see. In cameras, however, you can see that this number is much higher. So in the most advanced cameras that we have nowadays, the back illuminated SCMOS, 95% quantum efficiency means almost all the incoming photons are actually detected. And why do I write here the peak? It's because the quantum efficiency is different depending on the photons, depending on their wavelength. So you can see in here that for a conventional PMT, for example, that there is a higher quantum efficiency, the 35% is only in the blue range. And then it just goes down and down and down as we go to longer wavelengths. Now in gas detectors, like this, for example, depending on the GASP, some of them are more efficient in the longer wavelengths and less efficient in the mid-range, let's say, wavelengths. And then others are very efficient in the middle of the visible spectrum, and then they go down quite quickly. This is the reason why when you have in your point confocal, if you have different detectors, they are likely to be a little bit different for those that are supposed to receive the blue light and those that are supposed to receive the red light. They are sort of optimized for these wavelengths. Okay, but you can see that the quantum efficiency anyway is not very high for detectors. So if we look, for example, at 800 nanometers, if we imagine a long wavelength, 800 nanometers, we have pretty much zero in these type in the GASP. Okay, but then if we use another one, then maybe we can get up to 20%. Means like 4 photons out of 5 are not detected. Now, if we look at the cameras, so in SCMOS camera, we can see that we have a difference between the front illuminated SCMOS, the back illuminated SCMOS, so the most sensitive or back illuminated SCMOS. And again, it's a curve like this. It looks like a much sort of steep curve, but it's just because the range here is very big. So basically, in the middle of the visible range, we can have a quantum efficiency of 95%, but as we go further away, for example, at 800, we're going to get with this back illuminated SCMOS, again, these are the best cameras, we get about 60%. So this is the reason why when we go into very long wavelengths, we need this to be quite bright because the camera does not collect so many photons. And in the EMCCD cameras, it's a little bit the same thing. So around 800, we can get up to 80%, but that would be sort of the top of the line detection in that wavelength. So you can see that all the sensors are actually not equal at all in terms of detecting photons and also across the whole spectrum that we use. So what about color cameras? Color cameras are a bit different. What they have is that they have what is called a Bayer filter on top of the camera. And we have filters, so these are emission filters basically, that are stuck to the camera, and they can be green, blue, or red. And in general, we have 2 times more green than red or blue. So you see we have more green here than red and blue. And why? This is mimicking the distribution of the green, red, and blue photoreceptors in the human eye. So these cameras are designed to mimic the eye so that when you look at the image, it's a color image, then you get the impression that you would have with your eyes. So they are very small pixels in general, but that is because you need 4 pixels to get one image, 1 pixel in the image. Okay, so we have 2 green, 1 blue, and 1 red that participate into 1 pixel in the image. So even though they have quite small pixels, the effective pixels that participate is actually 4 times larger. So the quantum efficiency can look like this. For example, you would have a different quantum efficiency for the 4 different colors. And like, for example, I say 65% or 70% quantum efficiency for these cameras. So now I'm going to talk about speed in a very quickly. So for detectors, we know that on a single point confocal, we're scanning pixel by pixel. Bloop, bloop, bloop. So this is slow. And we have a certain exposure time, if you want to say, per pixel. It's called the pixel dwell time. And this is measured in microseconds per pixels. So how long do we stay on each spot? And then integrate all these photons that come from the sample. And then the scanner moves to the next spot and then integrate, and measure all these photons from here. So how long do we stay on each spot is called the pixel dwell time. And then we know that we can image with lots of different pixels, and that depends on the scanner and the number of spots that we are deciding. We have chosen in the software. So if we have a pixel dwell time, for example, for microseconds, and we have we image in this way, so we have 2048 by 2048. So the image will take 17 seconds altogether. So you can see that it takes quite a lot of time when we have lots of pixels. And so we can help this by using the bidirectional scanning. So anyone who has a single point confocal can choose the number of pixels, can change the pixel dwell time, and in some software like in Zeiss, this is called the speed. But when you change the speed, you will see somewhere the pixel dwell time is written there, and you will see what it is. And then if you also have bidirectional scanning if you use a single point confocal. And that means that we are, instead of imaging going back to the beginning of the line, imaging going back to the beginning of the line, you are imaging. So it goes pretty much double the speed. So if we use these settings and we use bidirectional scanning, then we can get to 0.1 image per second. We can go faster with the resonance scanner as well. And also, we have different detectors because in a single point confocal, we always have more than at least 2 detectors and up to 34. So we can image several colors at once. So that helps us also go a bit faster. Now, if we try to compare with a camera, all the pixels are exposed at once. Let's say that we have an exposure time of 10 milliseconds, which is quite normal in a camera. Then you're going to have the same, if we have a chip that has the same number of pixels, so 2048 by 2048, we are now imaging at 10 milliseconds, we're imaging 100 images per second, okay? And we can change things a little bit by changing the readout rate. So if you have a camera, you will have something that tells you readout rate, and sometimes they give them funky names like speed or something like this. But basically, this is the readout rate is how fast the electrons are removed from the chip before we can acquire again. This is the readout rate. So you can say in here, the pixel dwell time is how long we stay on one spot before we move to the next spot. This one is how fast we acquire an image, and then we wipe off all the electrons before we expose again. So how fast can we do that? This is the readout rate. If you have a high readout rate, you're going to create noise, and we will talk about noise now. So that is a balance to be had between going faster, removing all these electrons quickly, or creating noise in the image. And in a camera, in general, you can image only one color at a time. So if we compare now with an image that is going to have 2048 by 2048 pixels, so acquired with these two sample or these two microscope. In this one, we're going to have 0.1 image per second, and this one we're going to have 100 images per second. That's 1,000 times, okay? And these are not outrageous settings at all. These are normal settings. So it's a camera-based system. It's definitely much faster. Okay, we can have several colors here compared to this one at a time, but you can see that the balance goes into camera-based systems being much, much faster. And if you can use the bidirectional scanning on single point confocal, do it. Sometimes the lines are slightly misaligned, and there is a way to align them. So depending on your scientific question and how precise you need to be, sometimes you can go bidirectional, just a line, and that's good enough. In general, there's always a tiny bit of misalignment left, and therefore, if you need to use the best resolution of the system and have the best definition of the image, you should use unidirectional scanning. And on the camera-based system, you should increase the readout rate if you want to go faster, but at the expense of the noise. So you're going to get some noise in the image. So this is the way we can change the speed, and we're going to have a little workshop about speed later. Right. So now, after this short, oh, I have like 10 minutes early. That is really cool for once. So I'm making it up for this morning. So we're a little bit early, and that's cool. I would like to know if you have some questions, and then we're going to do some quizzes in the